Okay, so I want to start out by thanking the opponent, the committee members, and the audience for coming to my defense, which will be about optimal security response in IT systems. So this is a security operations center where human operators sit around the clock and try to respond to potential cyber attacks. Currently, we have a global shortage of around 4.8 million of these operators. And this shortage really motivates the main question of my thesis, namely, how can we automate these operations? Or is it even possible? To illustrate this problem, consider the following IT infrastructure, which consists of a set of interconnected components that jointly provide services to a client population. This could be the banking service that you use to pay your bills. It could be the navigation service in your car, or it could be the payment service of your public transport. Often, these services are provided by IT infrastructures through a public gateway. And while this gateway is intended for service delivery, it is also accessible to a potential attacker who seeks to intrude on the infrastructure, compromise components, and disrupt services. So when such attacks happen, it is then critical that the operator of the infrastructure, which I'm going to refer to as the defender, quickly responds to the attack in order to mitigate its impact. For example, the defender can use flow control to dynamically isolate malicious traffic on the network. It can use access control to constrain the movement of the attacker, or it can use replication control to make sure that critical services remain available even when some components may be compromised. In my thesis, I demonstrate both experimentally and theoretically how we can control these response actions in an optimal manner. Now, for this presentation, I will not go into all of the details of my contributions in the thesis. I will leave that for the discussion afterwards, but I will focus on the bigger picture and try to convey to you the key insights behind optimal security response and the main advancements of my thesis. So in my thesis, I propose the following general methodology for optimal security response, which can be understood on a high level through the following picture. So the starting point here is that we have a target system, and that simply corresponds to the system where we want our response strategies to be operational in the end. The first step of my methodology is then that I take the configuration of that system and I emulate it to create a so-called digital twin, namely a virtual replica of the target system that runs the same software but on virtualized hardware. And that twin then provides me with a safe environment where I can run emulated attacks and response actions, and I can then investigate and see what kind of responses are more effective against different types of attacks. Such investigations generate a lot of measurement data, which I use to identify a mathematical model of the system, for example, a game theoretic model, based on which I then apply optimization techniques to compute a theoretically optimal response strategy, which I then experimentally validate on the digital twin. And if that validation is deemed successful, I may also implement it on the target system. This is a very general methodology in the sense that it is not limited to any specific identification method, any specific mathematical model, or any specific optimization technique. And throughout my thesis, I demonstrate how we can instantiate this methodology in a broad variety of ways, leveraging concepts from many diverse fields, such as game theory, control, causality, reliability, fault tolerance, and stochastics. To demonstrate these instantiations to you, I will present 3 case studies out of the 6 that are included in the thesis. First, I will show you how we can use this methodology to decide when is the optimal time to execute a response action against a potential attack. Then I will show you how we can use the same general methodology to withstand or tolerate cyber attacks in an optimal way. And finally, I will address the question of how do we respond to a cyber attack when we are uncertain about the very nature of the attack to begin with. So let's start with the simplest possible instance of the security response problem, where we only have a single response action. For example, blocking the public gateway of the infrastructure. In this case, I formulate the problem mathematically as an optimal stopping problem, where the defender observes the infrastructure through security alerts, which we can think about as a stochastic process. And while observing this process, the defender then has two options at each time step. So it can either decide to continue to monitor, or it can stop and take the response action, or block the gateway in this case. And the question is then, which point in time here is the optimal stopping time? This can be formulated as an optimization problem, where we want to find a stopping time tau that maximizes some given objective function j. And this objective could be, for example, that we would like to stop the attack as soon as it starts, but not before that moment. Such an objective then gives rise to a very simple dynamical system that starts in the healthy state, and at some unknown point in time, it will transition to the compromised state. And once that transition has occurred, we would like to stop the system as soon as possible. Now, the challenge here, of course, is that we cannot directly measure the state. We can only measure noisy observations of the state in the form of security alerts. And this means that in order to decide when is the optimal stopping time, we need to have statistical information about how the observations depend on the state of the system. And this is where the digital twin comes into play in my methodology, because it allows me to collect empirical measurements of these observations, both during normal operation, that you can see in blue, and during attack, that you can see in red. These observations then allow me to estimate the observation distribution, based on which I can compute the so-called belief state, namely the posterior probability of being in a current state, given the history of observations. And since the state here is Markov, and the belief state is a sufficient statistic of the state, I can then frame security response as the problem of mapping a belief to a response action. And in the simple case, when we only have a single response, this problem has a particularly elegant solution, as I prove in the thesis, namely a threshold solution, where the optimal thing for the defender to do is to monitor the infrastructure, update the belief, and when the belief reaches to some thresholding point, that is when you should trigger your response, or block the gateway in this case. The nice thing about this strategy is that it's very simple to understand, but the drawback is that it's a bit too simple, because it's quite limiting to only have a single response. And consider now the more general formulation, where we have L response actions, where L could be in the hundreds or even the thousands. In this case, we have an optimal multiple stopping problem, and the goal is to find L stopping times instead of one. And I show in the thesis that in this case, we can generalize the previous theorem and establish that the solution is a multi-threshold strategy, where we have L thresholds, one for each response, and these thresholds are decreasing in L, such that the more response actions that you have left, the lower the threshold will be. And as you take response actions, the threshold will gradually increase. And in the extreme case, when you only have one response left, for example, blocking the gateway, then you will have the largest threshold, which I think is quite intuitive. Now, this theorem was actually very challenging for me to prove, but the benefit of having this insight into the structure of the optimal solution is that it enables me to very efficiently compute and implement this strategy in practice. And that is exactly what I have done. On our testbed at KTH, which is located just a few hundred meters away from here. And on this testbed, I then deploy the following IT infrastructure. And to test my threshold strategy, I simply run a series of attacks against this infrastructure, virtual infrastructure, and then I try to measure and see how well does the threshold strategy respond to these attacks. So how well does it mitigate them? And here are the results. So what you can see here is that after around 1 hour of computation, so 1 hour of optimizing the thresholds using my methodology, I obtain very close to optimal performance, both on the simulator that you can see in red and on the digital twin that you can see in blue. And this took me many, many hours in the lab in order to narrow this gap. But now when we have this tight gap, this can give me very high confidence that this threshold strategy would also perform as expected when we deploy it on the target system. Which of course I cannot measure directly because it would be unsafe to run attacks against an operational environment. And while I have focused on a pretty simple response scenario here, this is still a key milestone in my research program, because this is the first demonstration of provably optimal security response on a practical IT infrastructure. This can be contrasted with a lot of the prior research in this area, which often either work more on practical access, but then are completely devoid of any notion of optimality, or work more theoretically, but in many cases lack practical applicability. So with this result, I'm essentially pushing the boundary of what we can achieve when we traverse both of these two axes at the same time. And now I will show you how we can go even further in that direction by applying my methodology to a very practically relevant use case, namely intrusion tolerance. So here I consider a distributed system that provides a replicated service to a client population. And I want this system to be intrusion tolerant in the sense that even if an attacker would compromise a subset of the replicas, the system as a whole should continue to operate correctly and maintain service to the clients. This problem can be understood on a high level through the following picture, where on the x-axis you have time and on the y-axis you have system performance. And at some unknown point in time, indicated by the left dotted line, an intrusion event may occur. And when that happens, we want that the system maintains some acceptable level of performance and as quickly as possible recovers to normal performance again. Building such a system requires three main components. Firstly, you need to have an intrusion-tolerant replication protocol that allows your replicas to coordinate themselves and reach agreement on the response to a client request. Secondly, you also need to have a replication strategy that tells you how many replicas to use. And obviously, the more replicas you have, the more failures you can tolerate, but that also implies a higher cost. And finally, you also need to have a recovery strategy, because no matter how many replicas you have, if you run the system long enough, then eventually all of them are going to fail at some point. Despite this obvious fact, if you look at traditional intrusion-tolerant systems, they did not do any recovery and only used a fixed number of replicas. Then, around the year 2002, we had this seminal paper by Castro and Liskov, which introduced the idea of proactive recovery, where you recover your replicas at periodic time intervals. And most of the systems developed after this paper was published follow the same idea. So they also use proactive recovery and very simple heuristic replication strategies. Now, the main question that I'm interested in is, can we do better than these heuristic strategies by applying my methodology for optimal security response? And to answer this question, I propose the following control architecture for intrusion-tolerant systems, where we have a set of nodes that are coordinated through a consensus protocol. And each node is segmented into two domains. So we have an application domain where we run a service replica inside of a virtual machine. And then we have a privileged domain where we run a controller that monitors the replica and decides when to do recovery. In addition, we have a global, what I call a system controller, that manages the replication factor and performs failure detection. And we say that this system here provides correct service to the clients if every request sent by a client is eventually executed and all of the healthy replicas execute exactly the same sequence of requests. Now, by introducing some standard assumptions on the synchrony of the network, it is then possible to prove, as I do in the thesis, that the system will guarantee correct service as long as the number of failed nodes is upper bounded by f and the total number of nodes is at least 2f plus 1. These invariants can then be thought of as two control problems, where the first one relates to intrusion recovery. So we need to make sure that we do recovery quickly enough so that we never reach this threshold f. And the second one relates to replication control, where we need to ensure that we always have a sufficient number of replicas so that we never reach, so that we always maintain this inequality here. And in my thesis, I formulate these two control problems as a two-level game, where on the local level, we have node controllers that perform intrusion recovery, and on the global level, we have a system controller that manages the replication factor. And based on this game theoretic formulation and the associated analysis that I present in the thesis, I then obtain the following analytical result, where on the x-axis here, you have the KL divergence between the feedback distribution during normal operation and during an attack. So essentially, a larger KL divergence means better intrusion detection. And what you can see here is that if you do not have any intrusion detection, then periodic recovery is optimal. But as soon as you have some signal, and by no means does it have to be perfect, then the cost of my methodology very quickly goes down. So at least in theory, if you have an intrusion-tolerant system that is equipped with sensors and monitoring systems, there is a significant benefit of optimizing the recovery strategy using my methodology. And similarly, if you look at the global level, here on the x-axis you have time, and on the y-axis you have service availability. What we can see here is that if you're only going to run your system for a short period of time, it does not really matter what replication strategy you use. You could equally well use a fixed replication factor. But if you're going to run your system for a long period of time, you really need to do adaptive replication in order to ensure service availability. And again, in that case, in theory at least, there is a potential benefit of using my methodology to optimize the replication strategy. Now, this is what I can say about the problem theoretically, but let us now also validate this experimentally. And the idea here is very similar to before. I take my intrusion-tolerant system, I deploy that on our testbed, and then I run a series of attacks against the system, and I try to measure and see how well does the system tolerate these attacks in terms of service availability and in terms of operational cost. And here are the results. The red bars relate to my methodology. The blue, pink, and green ones relate to the baselines. If you start from the left column, you can see that in terms of service availability, there is not a huge difference between my methodology and the baselines. There is a small difference in my favor, but it's barely noticeable in this figure. On the other hand, if you look at the middle column, then we can see a very noticeable difference where my methodology achieves a much, much lower time to recovery than the baselines, which is not so surprising because most of the baselines are based on periodic recovery. So they always have to wait an entire period before they can trigger the recovery, whereas my methodology is based on feedback control, so we can trigger the recovery as soon as we suspect an ongoing attack. Finally, if you look at the rightmost column, you can see that the recovery frequency is about the same for all strategies. You could have expected a higher frequency of my methodology since it had such a low time to recovery, but that is actually not the case in my experience. So the takeaway here is that by applying my general methodology for optimal security response on an intrusion tolerance use case, I've been able to build the first intrusion tolerance system that is provably optimal and can formally guarantee any chosen level of service availability. However, there is one issue here that I have overlooked and that I will address in my final case study, and that is what happens when our assumptions or our mathematical models are incorrect. So the reality is that IT systems are so complicated that whatever model you use, it will never be a perfect fit of reality. So there will always be some degree of what we call model misspecification. And in this case study, I will show to you how we can manage and how we can quantify this misspecification in the context of security response. So if you look at prior work in this area, including my own prior work, then the standard approach to optimal security response is that you start out by creating a mathematical model of your system, and then you make this silent assumption that the model is correct. And under that assumption, you can then solve the problem offline, numerically or analytically. But what if that assumption is not true? And what if your model is misspecified or even non-stationary? So I present a solution to this problem in the thesis, which I call conjectural online learning, which is an online method for learning response strategies where the defender does not need to have a perfect model. It only needs to have some probabilistic conjecture about the model, and that conjecture may even be misspecified. The method involves two main parts. Firstly, we use Bayesian learning to adapt the conjecture based on feedback. And secondly, we used rollout to update the strategy based on the conjecture. So at each time step, the defender will take a response action, and this could be the null action as well. Then it receives some feedback from the system, for example, security alerts. And based on that feedback, it would then adapt its conjecture using Bayesian learning, which results in a posterior distribution over possible models, from which the player or the defender would then sample a particular conjecture and use that to compute a new strategy using rollout. And I prove in the thesis that in this case, we can actually bound the performance difference between the rollout strategy and the optimal strategy. And we can also guarantee that the Bayesian learning will converge to a set of conjectures that are consistent, but not in classical Bayesian consistency, but rather they are consistent with the observed feedback in the sense that they minimize the KL divergence between the observed feedback distribution and the distribution that is induced by the conjecture itself. So to illustrate this convergence, consider the following time series. The black line indicates the conjecture distribution, and the dotted red line indicates the true model, which is just equal to 1 in this case. It's just a scalar. Now, if you start from the top left here, you can see that the defender in this case starts out with a uniform prior between 0 and 0.8. And then we say that the defender is misspecified because it assigns 0 probability measure to the actual model. Then over time, we are doing conjectural learning, and you can see that the conjecture distribution is moving closer and closer to the dashed black line, which is the set of consistent conjecture. Now it just happens to be in this very simple example that the consistent conjecture is a singleton, and it's also closest in the Euclidean sense to the true model, but that does not have to be the case in general. And this convergence can lead to very interesting game theoretic equilibria, which we call the Burke-Nash equilibrium, where both the attacker and the defender have some conjecture of the system that may be misspecified, but that is consistent with their own feedback. And then they act optimally based on those conjectures. So that can lead to steady states where the attacker and the defender have completely different perceptions about the system and about the vulnerabilities or the security state, but they are still in some kind of equilibrium with each other. And I prove in the thesis that if my method converges, or when it converges to this equilibrium. Unfortunately, I also prove that this equilibrium does not always exist. So it depends on the stationary distribution existence in the belief space. And that is what I can say about this method theoretically, but let us now also look at some experimental validation. So for this experiment, I used the following target infrastructure, and I defined the hidden model to be the distribution of security alerts that is generated by this infrastructure. And I defined the response action to be the blocking threshold at the gateway. So the gateway can block IP traffic based on security alerts and the severity of alerts. And by defining the response action in this way, I can then make a direct comparison between my method and an industry standard, namely the SNORT intrusion prevention system, which is a rule-based system that does exactly the same type of blocking at the gateway. And here are the results. So what I find is that if I configure SNORT in the right way, I can obtain exactly, or more or less, exactly the same performance with SNORT as I do with my method. But as soon as the system changes, or there is a substantial change in the feedback distribution, then SNORT starts to perform very poorly, whereas my method, shown in red, can adapt to the change and update the conjecture over time. So the takeaway here is that this type of online learning can provide a much higher level of automation than what SNORT requires, which requires to be manually reconfigured whenever the system undergoes a substantial change. It's also the first method for learning response strategies which explicitly accounts for model misspecification. And that concludes my 3 case studies. And now to summarize what I've just told you. In my thesis, I studied the problem of automated and optimal security response. I started out this presentation by showing a general methodology for achieving this automation. And then I presented 3 case studies, in each of which we instantiate this general methodology with a specific formal framework and apply it to a certain instance of the problem. And through these 3 case studies, I have then proven, experimentally and theoretically, that it is possible to build an automated system for responding to cyber attacks in real time in an optimal manner. And the main takeaways are that the digital twin is a necessary component for optimal security response. This is what drives the whole methodology and enables us to narrow the gap between theoretical optimality and practical applicability. Another key finding is that theoretical structures are very important, not just for intellectual reasons and understanding, but also for computational purposes. So I show throughout the thesis that by applying the right mathematical tools and exploiting this structure, we can very often significantly reduce the computational complexity. And finally, I also find that stochastic approximation is a suitable method for doing these computations because it allows me to circumvent the interactability of dynamic programming while maintaining certain optimality guarantees. So in conclusion, optimal security response has the potential to address many of the pressing challenges that we see in cybersecurity, such as the shortage of security operators, the growing complexity of IT systems, and the escalating frequency of cyber attacks. And the part of my solution that I want to emphasize is not the particular theorem or the particular algorithm, but rather the general methodology and the integration of engineering principles for self-adaptive systems and digital twins with mathematical models for theoretical understanding and numerical computations. And while there is still a lot of work left to do to fully operationalize this methodology, I believe that it provides the foundation for the next generation of security response systems. Thank you for your attention.